In this video, we investigate the concept of successive ionization energies of atoms. That is, the first ionization energy, the second ionization energy, the third ionization energy, etc. Previously, we used this graph to show the ionization energy values for the first 86 elements from hydrogen number 1 to radon number 86. And we saw that the general trend in ionization energies was that they increased going from left to right across a period and increased from bottom to top going up a group. The ionization energy shown in this graph are values for the first ionization energy. The first ionization energy is the minimum energy needed to remove the highest energy or outermost electron from the neutral atom in the gaseous state. But we know that electrons can be removed successively, and more than one electron can be removed from a neutral atom. The second ionization energy, I2, refers to the energy required to remove a second electron from an atom. And the third ionization energy, I3, refers to the energy required to remove a third electron from an atom. In general, the first ionization energy is smaller than the second ionization energy, which is smaller than the third ionization energy, and so on. And this is because as electrons are successively removed, the remaining electrons experience a relatively greater attractive force to the nucleus, since the number of protons is now greater than the number of electrons. As a result, remaining electrons are more tightly held, and removing successive electrons costs more energy. This table shows the successive ionization energies for the period 3 elements. Note that there is a sharp jump in ionization energies from the first to the second ionization energy for sodium, corresponding to the removal of inner or core electrons. For example, removal of the single 3s electron from the third shell of the sodium atom only requires 495 kilojoules per mole of sodium atoms. Removal of a second electron from sodium costs a lot more energy, and this is because it involves the removal of a core electron from the second shell, which will disrupt the stable inner core electron configuration of neon. This is why the sodium atom will only form the 1 plus Na plus ion. We see a similar pattern when we look at the ionization data for magnesium, atomic number 12, with 2 electrons in its outermost 3s subshell. Removal of the 2 electrons from the 3s subshell of magnesium costs relatively little energy. However, removal of a third core electron from the second shell, which disrupts the stable neon core electron configuration, sees a very marked increase in energy. The stable ion for magnesium is therefore the 2 plus Mg2+ ion. A similar situation exists for aluminium, atomic number 13, with 3 outer shell electrons. Removal of the 3 electrons in the third shell costs considerably less energy than removal of a fourth core electron from the second shell. The stable ion for aluminium is therefore the 3 plus Al3+ ion. Beyond aluminium, we can see that the energy required to form a stable cation with the neon core for period 3 elements starts to become prohibitively high, which is why the silicon 4+ ion or the phosphorus 5+ ion will not normally form during chemical reactions. The 2 take-home messages from this table is that successive ionization energy values increase in value going from I1 to I2 to I3, etc., and that sharp increases in successive ionization energies where core electrons are removed can be used as an excellent guide as to which stable cation will likely form.